I know it's kind of weird to ask. Would there be any objections to holding Thursday's class online? Reason being is that my wife is scheduled for a booster shot today, and it will just make the mechanics of, she'll be scheduled for a booster shot on Thursday, and it'll make the mechanics of getting that done a lot easier. They can just be at home, and since again, I'm not going to be taking any demos, and I'll be just doing, this recording stuff. Sorry, this lecture review, this final exam review. Does that sound good to everybody? I'll send out an announcement. Okay. Also means you get to stay home, not have to brave the cold, early in the morning. So, okay. I'll also send out announcements as to when the exam is. It's just to remind you guys. And again, if you have any issues, please let me know. Okay. So with that, we're going to look at a couple of, we're going to start by, so first off, in the GitHub repository, the public one, if you go to destruct, or for short for data structures, and you go to, if you click on the folder, down here is a study guide that I wrote a while ago, back in 2017. And you'll see these are basically, I've listed pretty much everything that we've went over and you'll need to know for the final exam. Although Huffman encoding, we do not need that. So big O notation, recursion, especially as it relates to trees, because trees and recursion, that's the easiest way for me. Why test two topics independently when I can test them both at the same time, right? Sorting, specifically with sorting, we need you to know insertion sort, quig sort, and the partition operation, as well as merge sort. Know why we would why do we want to use each of those three algorithms, and why don't we want to use each of those three algorithms, okay? Because those are the big ones that are used. Pretty much everything that is used these days is a variation on quick sort or merge sort. Maybe not the quick sort you learned in class, right? The Java uses a double partition quick sort, but that's still quick sort. It still works the basic same way, right? It's just a variation of it. And merge sort, same deal. All right. Then for the data structures, you do not need to write any data structures. You just need to know how to write the code that uses them. So with linked lists, right, you'll be wanting to write you'll be wanting to write code that creates linked lists. You don't have to access, in fact, though, but you do not want to be using any nodes if they're linked lists. For the trees, I'll be giving you nodes, but for linked lists, don't interact with the nodes. That's going to make your job harder. You want to know how, with linked lists, how to do the add, removes, and all that stuff, and make sure that it works in the proper way. Stacks, queues, know the basics of that. Trees, the heaps, and hash tables. Also note about the just like in exam 2, there's going to be a multiple choice section where I want you to select the answer to the multiple choice, to the best data structure that fits. Okay. Also here, you won't be able to click on them here, but while it's embedded, but if you actually go ahead and download this PDF, you click download, you'll be able to get to the links here of some final exams from other institutions. The first one is broken, unfortunately, but I remember the big question from it. But the other two, some of them are more algorithm. They lean stuff into the algorithm stuff. Aha, they've taken that. I'll have to fix that one. Okay, so there's only 2 of them, but that's okay. We're going to be going over this one though, because let's see, they have changed it over time. They have changed it based off of, okay, this is a new exam that I've had. So I haven't done this one before. Let's go ahead and do this one. That'll be new for me. So that's what we're going to do today. We're going to go over other institutions practice exams. I will be skipping over anything that I deem not relevant to the exam. Okay. So, all right, multiple choice questions here. This is a boring question. I don't need this one because if you're doing this on a computer, you know, what are you going to know? 2 times mystery. So this is going to be just what? Give you quadratic amount of, yeah, this would give you, so this recursive method looks like your standard power of 2 kind of deal, right? So you pass in n, if it's greater than 1, then we return 2 times n minus, we'd return 2 times 2 to the nth minus 1. Once it gets to 1, though, we're not returning 2, we're returning 1, which is the trick there. So 2 to the 1 returns 1, whereas it should return 2, right? So this will return, so you can test that. I'm not going to even bother testing this. I'm going to guess, no, I'll test it. I'm going to guess that this answer is 4 because it's going to, because we've got a terminating value at n less than or equal to 1 is our terminating value and it returns 1 rather than 2. This is going to be our, this return calculates n, 2 to the n minus 1th power rather than 2 to the nth power. Let's go ahead and create our Java class to slap all this stuff in. That looked ugly. Oh, didn't like the, surprisingly, it's okay with everything else but the, but if, okay, surprisingly, it's okay with that because Java doesn't care about white spacing. So Sout mystery 3, that should be 4, I'm guessing. Yes?
Where did you get the link to this one? I think this is a link that doesn't work.
Yeah, I found this one by Googling Harvard practice exam data structures
Okay.
before I pulled stuff up. And let me make sure I'm right. Yeah, I'm 4. Awesome. It's good to know. All right. So here, from the vehicle, given the vehicle classes from lecture, which we don't have, which of the following appropriate assignments statements would not compile? So we don't know because we don't know which of them are this tractor trailer would not compile because a tractor trailer is a type of truck. So it's the other way around. You'd want to put truck T is equal to new tractor trailer. Same with automobile A. A taxi is a type of automobile, so that's fine. A moving van is a type of vehicle. And here, a moving van is not a type of truck. So I would assume that doesn't compile as well, assuming we can get multiples of them. So given the vehicle, so okay, and then we'll continue on again to stuff. All right, let's move on to this other stuff. These are a lot of the same questions from the other one, but it's reordered. Okay, with a poorly chosen hash function, it is possible to have the situation in which the search time of a hash table of n items goes to which of these? So which is the worst case with a poorly chosen hash function? What is the search time? Yes.
I think all of that.
That's correct, O of n. So let's go ahead and create a poorly chosen hash function just to kind of demonstrate. And we can create a poorly chosen hash function where I say h of x, where x is our key, is equal to 0. And then resolve using, either using, linear probing, open addressing using linear probing or via chaining. Either of those results in an O of n runtime. Because we'd look at the first spot. Oh, the first spot is taken. So I'm going to go to the next spot. Okay, I'm there. Now, if every time I add an item, it's going to go to the next spot. It's just a complete unordered mess, So that's what a poorly chosen hash function does. It results in a unordered mess that just simply means we now have a list that we've created a list with extra steps, except that we can't actually even use list indices. So it's technically not even a list. It's just a mess. right? Collisions are what kills us for hash tables. All right. Oh, I like this one. I remember this one. All right. A binary tree is constructed of nodes that are instances of the following class. Node, left, right, and instead of doing generics here, right, because not every school teaches generics, instead has integers in it. So let's consider the following method. Okay, let me zoom in too. Page width, there we go. Consider the following methods. So we've got our root node, right? It's no different other than it's using a int rather than a generic. Bulk stack note mystery. If root.right is null, return root. Otherwise, return root.right. So we're going to consult 3 supposedly tech-savvy consultants, and we get the following 3 opinions about what the method does when we pass a reference to the root node of a binary search tree. Or sorry, of a binary tree. It doesn't have to be a binary search tree. Consultant 1 says that if this method will return the last node visited by an in-order traversal. Consultant 2 says it returns the last node visited by post-order traversal. And it returns, and consultant 3 says it returns the last node visited by a level order of traversal. Which of these opinions is correct regardless of the contents of the tree? So so we want to know. So first off, we need to find a new term, which is level order traversal. They just mean breadth first search. They mean the kind of traversal we would do if we wanted to get stuff out of a heap, right? Here is level order traversal, right? So right now I'm going to go ahead and draw a perfect tree, and let's go ahead and just kind of figure out what we can from there. After we get a perfect tree, we'll be looking at more imperfect examples and see what we can modify from there and see how that changes our answers. But a perfect tree is good for just understanding how this works. So if we pass in the root node, if root.right is equal to null, that's not the case here. Root.right exists. So otherwise we're going to call mystery on this guy. So this says, hey, if root.right is equal to null, well, it doesn't. So we're going to, so my right node exists. So we say mystery on root.right. So in other words, if the root.right exists, call mystery on it. So we're going to keep, so this calls mystery on this, which calls mystery on this. And now it has no right node. See, root.right is equal to null. So it's going to return root, which says to return root, which says to return root being this guy. So it's returning this guy here. So now let me clean that up. So it returns the last node visited in an in-order traversal. Is that the case? What is the last node in an in-order traversal? That's the last item in a tree, right? In order gives things from least to greatest. It's the sorted order. And the biggest item is always the rightmost item, right? And so no matter what, so this worked here. Last node visited in a post order. What's the last node visited in a post order traversal? Or what is the lasting output? That's how I'm going to assume they want. The last node visited by post order traversal. Yes.
I think it's the root.
Yeah, I'd say it's the root of the last node is visited by a post order. That's what I mean by I'm going to assume by visited that it's going to be like the last one to resolve. It's not fully visited until you resolve all the calls for it. Because you could argue that this would be the last. Sorry, that this is the last thing called in the post order. It really depends on what the instructor is intending there. And I think that's, again, kind of a vocabulary thing that with different assumptions in class. So again, if you kind of get these things for interview questions, ask questions for elaboration because human language is imprecise, but code isn't. So mystery. So this is the return the last node visited by this. We want to return this, and depending on the definition, this is or is not the last node. Now, level order traversal, this would be this one, then 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 this one. It's left to right across the ordering, right? It's breadth first search. So we didn't teach it because not done using recursion. Right? It's breadth first search. That's how you do it. And so we learned that in how to do graphs. Okay, so it's going to return this one, and it works for this case. But if we go ahead and alter this now, let's alter this graph. So if we alter this tree, root.right is equal to, so this is going to return the rightmost node in the tree, right? The node with the greatest value. So for one, it still works, right? This is the rightmost node. This is what it's going to return. The last node visited in a post-order traversal. So if it's this node, so start here, then, so I visit my left. So post-order means handle my left, my right, then myself, left, right, and self. So here, right, it's going to either return the root or the last node visited. It would be this one, depending on how you look at it, whether you're looking at your visited order or your finished order. Finished order is like when they would be done going through with that node, right? But if we're visiting, we'd start here, then we'd call left, and then we'd call the left. And this one would say, we're here, call my left, then call my right, and then finish myself. We'd be here, call my left, then call my right, and finish myself. So this one, either way interpretation, it's not going to, if we're going by finish order, then this is the last node returned by finish order. If we're going by visited order, we'd visit this node first, and then this would be the last node visited by visited order, because we'd have to resolve this before resolving this. And so either way, it's not going to work. The last thing is a lot more trivial. So this is a lot more trivial. 1, 2, 3, 4, 5, 6. This is the last node that gets visited, which is not this node. So only Tech Consultant 1 is correct in this case. I also like this question. This one's great because it requires these kind of judgment calls you have to make. So a police department wants to maintain a database of up to 1,800 license plate numbers of people who receive frequent tickets, so it can be determined very quickly whether or not the license plate is in the database. Okay, so we want to create basically a database that holds are these frequent ticket recipients up to 8, and we want to hold up to 1,800 tickets. We don't want to hold any more than 1,800 tickets. Speed of response is important. Effective use of memory is also important, but not as important as the speed of response, right? So we care about time more than memory, but we still care about memory. Make sense? Which of the following data structures would be most appropriate for this list, for this structure? So let's go through them one by one. A sorted linked list. In a word, that's terrible. And any programmer who suggests that this solution should be involved, that the solution to this is a sorted linked list, should be fired into the sun. And this is because when you're looking through a sorted linked list, the only way to find a specific item in a sorted linked list is to do an O of N search, right? Because there is no such, because if you're going to do if you try to do a binary search on a sorted linked list, you're going to iterate through to get to the halfway point, and then you got to iterate to get the other halfway point. And it ends up being a lot more effort than just to go search through all N items. Takes O of N time to find something in here, and it's going to take, O of N memory. Always going to be pretty much O of N memory, but it's all about the amount of overhead, additional overhead that we're going to incur. All these solutions involve O of N memory. It's just the amount of overhead we're going to incur with pointers and stuff. And here we would have, the nexts and the previous's. A sorted array with 1,800 entries. Well, this is about as good as it gets. In terms of memory, if we cared about memory, this is literally not constant, but it's a constant space of how much auxiliary memory we'd have to use searching for something in there, which is we'd have to hold a couple variables worth of memory. And there's no additional links. We're just storing the items in the array, which is great. The amount of time to find something in a sorted array, you use binary search, right? You start at the middle, is it greater than or less than, and then recurse, which takes log n time to find if something's in there, which is awesome. Okay, a balanced binary search, so a balanced search tree, where I'm going to assume binary in this case, that's also log n, right? If it's balanced, it takes log n time to find something if something is in there, which is great. It would take a bit more memory though, because you have references, right? Whereas this has reference. Oh, he removed one that he thought was a bit ambiguous, interesting, and replaced it with the balanced binary search tree. I'll put in the other one. It's a good exercise there. So that's option F, which is wrong because obviously if you take it off, it wasn't the right answer. But but it's good to understand why that is almost correct. So a balanced binary search tree, right, also takes O of log n, but the memory cost is a bit higher than this because, well, whereas we don't have to keep any links for B. In C, we'd have the left and the rights, and all nodes would have the lefts and the rights, and they would have the node containers themselves, which are their own memory cost. Whereas again, with the array, with arrays, that keeps the memory cost as low as possible. All right, hash tables. So now, as you can imagine with hash tables, ideally with hash tables, we get constant time, right? If you remember, it's O of 1 with an asterisk, right? It's amortized, meaning on average, it takes, the cost of doing this is cheap. But let's look at this. Using a hash table using open addressing with 1800 entries. So that means that our hash table, the size of the table we are using is set at 1800 spaces. And we want to put 1800 things in there. Now, I'm going to go give you the non-mathematical definition because I'm sure you're all tired right now of why this is a bad idea. And then I'll go ahead and look for the math reason why this is a terrible idea. Okay, imagine you're trying to park a car in a parking deck and it has 1600 spaces, right? And that 1599 of those spaces are taken. So you're trying to find the only empty parking spot in that parking deck. How long is that going to take? More time than it's worth, right? It takes forever to find that last parking space. And that's exactly what's kind of happens there. That's 1800, but whatever, you get the point. The point being is that basically when a hash table is full up, that means that the number of collisions it's been having, and not car collisions, but collisions in the sense that we're looking for something and we can't find it, and we can't find the space we wanted. So now I have to go and look for your space. You know how your father, he always looks for that perfect spot, and he just doesn't take the one right there and goes up and because he wants to be at the certain floor somewhere. It's kind of like that. And then it turns out like there's no spaces there and he should have taken the earlier one. And now it's all awkward, and if you bring it up, the family trip is going to be ruined. So so that's the kind of space what we're dealing with here. We're looking at it. It takes constant. It goes from constant time to O of n time to find your solution because you have as many spaces as you want. What makes hash table work is that you have enough space to avoid collisions, right? It's like, again, with traffic. Roads are great because unless everybody else is using them. Once it's full, you get traffic and everybody slows down. Or it should at least. Okay. Whereas a hash table using open addressing with 3600 entries, well, what if that parking garage is half full, right? No time at all to find a space. There's plenty of spaces. You just take one, right? That's exactly what's going on over here. Now, with regards to what in the world is this? Let's see. Knuth open addressing equation hash tables because I always forget it off the top of my head. Oh yeah, here we go. So Donald Knuth, who he wrote, let's see, so where is that? I'm just trying to find it. Knuth load factor. I'm just trying to find it because I always forget it. I always get it close, the equation close. So number of probes. Then number of probes for an unsuccessful search is 1/1 minus. Yep, here we go. So it is, here we go. 1/2, 1 plus 1/1 minus, there we go. Yeah, I remember this now. And minus alpha. It's so obviously it's scary because it's got a Greek letter in it, right? But what it's saying is that the amount of time it takes to find something in here is that it's, and I think I went over in the slides, it's 1/1 minus the load factor. That's what alpha is. In other words, what is the maximum amount this is going to be full, right? The load factor is n minus m here. So that's just how full this is. So, and so obviously, as you can see, and this approach is 1. So as we get closer and closer to 1, the worse this is going to get. So let's take a, so let me go back to my example. So in other words, let me go ahead and clear this. So in other words, right, with this one with 1,800 entries, let's assume that basically it's almost all the way full, which is, so we would do, so the equation is, and this, so what is this equation? This is the number of expected number of probes that we would have to do. The expected number, that's what that equation gives us, the expected number of probes. The expected number of probes we'd have to do is 1/1, sorry. Yeah. 1 minus 1/1 minus the load factor, which I'll just simply put as L because that makes it a lot less scary. Now that we're away from Greek, okay, and then 1/2 of that because on average you're going to be doing some long stuff and some short stuff, but so the expected number is going to be half that. So what is the load factor in this case? Well, let's assume that that we have 1,800 entries, right? So let's assume that instead of storing 1,800 license plate numbers, we're doing 7. Okay, we're doing 1,799 of them. Okay, so the load factor in this case would be 1,799 over 1,800 because I don't want to have to deal with dividing by 0. That's the reason I'm doing this. So again, so let's go ahead and look at the calculator. So because this math is about to get really ugly. Okay. Okay, so 1 minus 1,799 over 1,800. Sorry, no, sorry. Have to do. Okay. Yeah, I know. 1 minus. Oh, it's a standard calculator. Boo. Scientific calculator, please. 1 minus 1 over, you know what? Screw it. I'm just going to do 1/1 minus 1 minus 17. Oh, come on. I'm really bad at this. So 17, you know what? Fine, I'll just do a piecemeal. 1,700 divided by this much is 0.999. So that will be, so this puts this denominator at so this becomes 0.999. So this gives us 0.001, right? Or something close enough to it, doesn't really matter. So however, we've got a decimal, which in this place, which makes, when we do the resulting division, makes the number really big. 1 divided by, I really should have just pulled up Python and did it in there. Why didn't I think of that? 0.001, right? That gives us 1,000. So 1 minus 1,000. Oof. So that does go negative, or is it 1? Sorry, was it 1 plus? 1 plus, not 1 minus. So it gives us 1,001 searches. So about 500 searches. Not that great. Okay. When it's always full. That's actually pretty terrible, right? So on the other hand, if we do the this one though, I can do off the top of my head. Sorry, or without 1 plus minus. So sorry, E I can do easy enough. 1 minus 1 over 1 minus 1/2. So at worst, it's going to be half the way filled up, right? Yeah, I know I'm boring you with math. Sorry. 0.5. So 1, which is 1 over 2, which this becomes, the whole thing becomes 2. So 1 plus 2 is 3. 3 over 2 is 1.5 times. So on average, 1.5 probes, right? So this is pretty much constant time. Now, what if we had 10,000 entries? In that case, we'd be looking at getting slightly better time than 1.5 searches on average, but at a much higher cost in memory. So that's why we don't consider that one. Okay. Let me keep going on. I know I just wanted to go through that example. We did this one in the first exam, so not going to really bother with this one. Okay, which of the following implementations of a data dictionary of n items could, at least in some cases, require n operations to search for an item? A binary search tree, a 2-3 tree, or a hash table. Okay, so a binary search tree, notice that it's missing the word that was up here for the previous one, which is a balanced search tree. That's the trick question there, and I hate trick questions like that. They don't really serve much of a purpose. Because while students can be smart, not every student can be cunning. Cunning is one of those things that is acquired by reading stories about tricksters and watching a lot of Bugs Bunny cartoons. Okay, not necessarily everybody's cup of tea. So so binary search tree, binary search trees, right? Worst case scenario for a binary search tree is, and again, as much as I love cunning and being able to, build up my students' ability to be cunning, is not an objective of the course. So binary search tree can be unbalanced. We could essentially get a linked list with extra steps. So it could require O(n) operations. So 1 could be that. Now, we didn't go over 2-3 trees, but 2-3 trees, I think I mentioned them briefly. 2-3 trees, right? They are, I'm just checking to make sure I'm correct on this. I believe they're a balanced search tree. Yep, they are balanced. So they are a self-balancing search tree. They're not binary, but they're a self-balancing tree. So they're going to be log of n worst case no matter what. Okay. And then the hash table, as we saw with one of the early questions, we choose a poor hash function, we get O(n) runtime. So 1 and 3. Huffman tree, we'll skip that one because that's on our exam. Okay. Ooh, I haven't done this one before. Oh, see, I'm happy I get new problems. A new chance for me to be proven wrong as the, okay. I dislike this first off because technically the pivot in quicksort should have been this guy, which is weird. Okay. Okay. So the following algorithm is to be, sorry, the following thing is to be sorted in ascending order. Following array is to be sorted in ascending order. Which algorithm causes the array to be ordered 52, 47, 25, 33, 15, 14, 74 in the sorting process? Okay. We're going to go through and do this one at a time. I'm going to first rule out the easiest one to rule out, which is selection sort. The way selection sort works is that we select the smallest item and move it to the front. So 52 is not the smallest item. Sorry, so we move the smallest item here, then we move the next smallest item over here, then the next smallest item over here, then the next one over here, and the next one over here. 52, at that point, the thing is that there are very few moves in selection sort. So it's very easy to rule out because 52 will never be moved here. It would just never would. If 52 moves, it would be moved into the appropriate place in the array, which would be second to last, right? Everybody agree with that? So can't not be selection sort. Okay, let's go ahead and do bubble sort. Bubble sort relies off of swapping. Again, and it swaps adjacent items. But again, we can look at this wonderful 52 over here, because that 52 reveals a whole lot about the sorting algorithm. Again, so basically it's saying, which is this going to be an intermediate state in the array? Is there any point during the sorting, is it going to look like this? Okay. And the answer is, and again, with this quick sort, initial pivot is equal to 33. I'm going to leave that one for last and possibly do that by process of elimination, because I'm not sure if they're following the partition algorithm, the in-place partition algorithm that you're supposed to. Okay, because for the in-place, you use the first item, at least the way we learned it. So bubble sort, we're going to be swapping adjacent items and bubbling them up. So the biggest item is always going to bubble to the top. So 52. So what's going to happen, right? We look at these and we swap them, and we look at these, and then we look at these, and then we look at these, and we look at these, and we look at these pairs. We look at every pair and swap them up. 52 and 74 will swap at some point, but 52 is the next largest item. No other item will swap with 52. 52 is going to remain in this location. It cannot be bubble sort. Okay, you don't have to go through the entire process. We just need to know. This one, though, we kind of annoyingly do have to do. So the thing we have to do for this one is heap sort. Okay, so first off, let me put this in a tree format. 25 or rather in a heap format. 25, 47. Yeah, I think it will probably be heap sort. Can already 33, 15, 74, and 52. And again, I haven't done this question before, so I don't think I'll get it wrong because I'm good at this. I've been teaching this for a while, but it's always a possibility. So feel free to call me out on it. Okay, so 25. So the next process is that we need to heapify. And what does that mean? That means that we need to heapify this. We need to actually turn this into a max heap. Okay, so turn this into a max heap. So remember, the way that heap sort works is that we want to turn it into a max heap, which takes actually like log n time if we do it this way, the way I'm about to do it. And then it takes n log n time to go through. It's actually quite good. It's actually quite a good thing because if you just need the first couple of items in it, then it will do that. So what we're going to do is start from the back and push everybody and push the items down. 52, and since these items can't be pushed down any further, 52, 74, 15, and 33 can't be pushed down any further, guess what? We get to go over here. Right, you can either start from the top and let everything bubble up, but then you have potential, but the potential number of operations is 0 potential operations over here, then 1, 1, and then 2, 2, 2, 2, right? Potential max operations. But if you start from going the other way and trying to push down rather than bubbling up, you have 0, 0, 0, 0, 1, 1, 2, lot less operations. So 52, 74, 15, 33 all stay in place. We need a 14. This is a max heap. So the bigger items float to the top. So 14 swaps to 72, 74. 14 goes down here. Okay. 47. again, the bigger items float to the top. Okay, let's see. Yeah, that's fine. And now we need to push 25 down as far as it can go. 25 and 47. So 47 goes over here, 25. Okay. So now let me redraw 47, 25, 74. What did I miss? Oh, right, did the wrong way. 25 should not have swapped with 47. 25, 47. We should swap with 74. So, yep, 74 should go over here. 25 should go over here, and then 25 needs to push down one more time to switch with 52. And what was that last one? 25. Right. Okay, now let me redraw this just to clean it up. 74, 47, 52, 53, 15, and then 14 and 25. Okay. And now what we do to do this, yep, it's heap sort. Okay, then the next thing we do to do this, to sort it, is that we remove the top item. We remove the top item. Now, how do we remove an item? We replace it with the thing in front. But that we can't just toss out this item. We're trying to sort it, right? We can't delete it. So what do? We kind of put it in, we actually just put it right here and pretend it doesn't exist. Right? And now we just still consider the thing a max heap, but we no longer consider this number to be existing. Sorry, 74. So now, again, it's a max heap. The tallest item will bubble to the top. 52, 5, and now if we look, 52, 47, 25, 33, 15, 14, 74. So it is heap sort. Okay. Insertion sort would have basically, again, it couldn't have been as insertion sort because this portion of the array or this subportion or whatever, the first item should have been basically with insertion sort. The first substring should always be sorted in respect to itself, but there's no initial substring starting at index 0 that is sorted in respect to itself. Like 52 and 47 is not sorted. There's no reason for 52 to be down there. And 52 is at the end. So honestly, it would be sorted it'd be the last thing to be put in as the sorting process in the insertion sort. So that doesn't make sense. And quick sort, choosing the initial 33, you saw I have my doubts about that. But also, even if we did do 33, this is not all the stuff less than, and this is not all the stuff greater than. It makes no sense for this to end up over on that side anyway. Yes, that was a lot, but this is why I like it for a practice exam. The questions I ask on the actual exam I don't feel like they're nearly as time consuming. I try to make sure that the time consuming questions are worth the number of points they should be. But I like this because this is a great review of all the concepts that we went over all semester. So, and you may recognize this kind of question, although this is not exact question from your exam, which is we have an initial. You're not going to get this kind of question again where you're asked to create a tree. You're just not, because we had exam 2, and I'm trying to do a more cohesive approach here. The binary search tree is shown below was constructed by inserting sequences of item into an empty tree. Which of the following sequences will not produce this binary search tree? So the way we do that is we just check. So 5 always has to be a root, then 3, then 4, that's fine. 5, 3, 4, 9. We're basically trying to make sure there's no gaps in the entries. 12, 7, 8, 60. That's not going to be the first one. That would be silly. Professor, he never, like, people never make their items the first one. Although, full disclosure, I do. And I'm a jerk sometimes when it comes to writing my exams. Because I don't care whether it looks randomized or not. I care if it's easy to grade, which is why on my first exam for my in-person exams that I did in 1051 and 1068, the first exam had like Boolean evaluations where you were supposed to evaluate Boolean expressions, and all the answers were true. All 5 of them. Sometimes they switch it up and make them all false. But point is, it makes it very easy for me to grade. And honestly, with all the exams you get, that's got to be at least one, statistically speaking. 5, 9, 3, 7, 6, 8, 4, 12, 20. Just remember that most of your exam writers are human, and they're also not trying to be particularly cunning. So they'll just try. So if they want to make something look random, or that's why a lot of things gravitate to B or C rather than, because it will be placed that way. Whereas I am cunning. I am a bit of a trickster, and I enjoy that aspect of myself. 5, 9, 7, 3, 8, 12, 6, 4, 20. Let's look at the last one. Make sure I didn't mess up somewhere, because we're looking for the one that will break, that will not produce this. See, this guy is making us go through all of them, I think. 5, 9, 3, 6. So there's our gap. That would change the structure of the tree, because we did the 6 before the 7. Okay, this diagram below suggests how we could implement a doubly linked list, which we maintain a reference to both double-ended lists. We retain a reference to both the first and last nodes in the list. Which of the following operations would be inefficient to carry out when there are a large number of elements in the linked list? Okay. Insertion into the end, which front refers? No, that's easy. Insertion at the end, which front reserves? No, that's easy. Deletion from the end, which front refers, and deletion from the end, which rear refers. That one's harder because you have to get to because since it's singly linked, so the key here is that this is only singly linked. If it's a doubly linked list, it's easy to delete the last thing in the list, right? You just go to the previous item, make that the tail, right? But here, we can't go to the previous item. So we have to go to the other, we have to go around the other way, which takes O(n) time to get to the next to last item. Make sense? So that's why that last one is harder to do than the other ones. Right? Adding to the end, no problem, because you've got the tail and you're taking the tail pointer and attaching it to the new node, right? Same with the front. You've got the head. You're not removing anything. You're just adding new links to things that already exist that you can access in constant time. Here, though, we need to manipulate this link, and we cannot get to this link coming out of 17 in constant time. Make sense? The following method operates on a heap containing strings. H.remove. What is the big O time complexity of this method in terms of n? Do 5 removal operations. Okay, so you've got a heap, remove. Each remove takes a log n time. I'm not really liking this one because if the heap is 5 size, then it would be n log n, but otherwise it would be log n because it's a constant time, right? Does that make sense? Right, because but here it's probably they're probably going for log n because you're doing 5, no matter what, this operation takes 5. You do 5 log n operations, and that 5 is a constant factor that we factor out, right? So it just becomes log n. Make sense? Okay. So given the string below, given the graph below, awesome. Which of the following is not a topological ordering of our vertices? Okay, so topological ordering, while not on the exam, is essential for your last assignment. Topological ordering. Right, and what is the topological sort? That is just simply like the kind of, that's the dependencies. It's like, it's what we use to figure out prerequisites and the order in which you should take your classes, right? Because things that require other things. Now you want to use Kahn's algorithm. Internally shout, imagine Picard shouting Kahn, Kirk shouting Kahn. Yeah. Morning, it's tough. Okay. Hey. So what we want to do, so basically what we need to do with Kahn's algorithm is we remove the nodes and all their outgoing edges as part of doing Kahn's algorithm. And what we want to do is basically we select a node that has no incoming edges. So we look for nodes with no incoming edges and we select and we try to go through them and we remove it from the graph. And then we just continue until we've got to visit all the items. Easier to demonstrate. Watch. So A, we can remove A. Okay. And then we can remove B and its incoming edge, right? Because it has no incoming edges now. Now C, it has no incoming edge, so we can remove that. D has had no incoming edges, so we can remove that. E hasn't had no incoming edges to begin with, so we can remove E as well. And now we can remove F and then G and then H, right? Make sense? It's almost as though that was designed in mind for this. We can also do it from the last one where we can remove D first and then remove E. The rule is we can only remove things that have no incoming edges. And I feel like a little kid because I'm getting to scribble. Then we can remove C, then we can remove B, then we can remove F, and then G, and then H. Okay, so let's look if there's an H before G. There is not. So let's do A, B, D, A, B, D, E, G, F, H, C. I think that works for its D. Now let's look at C. A, then remove C, then remove D, then remove B, then remove E, and I think, and then G, and then F, and H. Okay, what about B? A, then C, then B, A, C, B, then here we're trying to remove F, but we can't do that because it still has incoming edges. So we removed A, then B, sorry, A, then C, then B. Then we try to remove F, but you have to remove D and E. You have to do D and E first before you can touch F. Make sense? Topological sorting is cool. Not on their final exam. It's part of your final homework where you do have to implement Kahn's algorithm. So as you noticed, Kahn's algorithm does have give you multiple potential answers, but your homework is constructed specially so that there is one unique answer, only one possible answer. Make sense? So your homework is specially constructed for that, and that's why I use it as use that problem as a homework. All right, answer 4 of the 6 questions in space provided. Well, you're welcome to try all 6, but make sure to clearly indicate which you want us to grade. All right. So the initial array, okay, so the initial array below is sorted in ascending order. After the initial partition step of the version of quicksort discussed in lecture with quicksort with 36 as the pivot, how would the array be ordered? So I'm going to go ahead and just cheat to make this usable for our exams and stuff, because we like to select the first item as the pivot. So if we're going to use 36 as the pivot, what we have to do is that we have to move 36 over here. Make sense? And have to move 17 over here, which adds one operation to the whole thing, right? No problem whatsoever to choose the middle item as the pivot. We just make it the front item now. Okay. So to do the partition, so after the initial partition step of the version of quicksort discussed in lecture, with 36 as the pivot, how would the array be ordered? Okay, and the array would be ordered. So what we'd have to do is that basically, again, we are going to, again, let's draw this a bit better. 36. We are going to look up for the first item greater than the pivot and look down for the first item smaller than the pivot. Up from the front, down from the back. Make sense? Look up for the first item greater than the pivot, look down for the first item smaller than the pivot. Once you've seen them, if they have not crossed the beams, if they've not swapped places, if up is still first and down is still second, then we swap the items. 53. And so, whoops. So 12, 53 swap places. Now we look up for the first item greater and down for the first item that's smaller. Gesundheit. 36, 12. So now they have not swapped. So we're going to do 23 and 1. Look up for the first item greater than the pivot and down for the first item that is smaller than the pivot. The first item smaller than pivot is 17, wouldn't you know? So we swap them. 17 and 62. Okay. And now we look up for the first item bigger than the pivot, which is 62, and down for the first item that's smaller. And now up and down have swapped places. So now what do? We swap 30 to finish this off. We swap to put this in the middle. We swap 30. We swap our pivot with the middle with this item. So we put 67 over here. So sorry, no, we put not 67. 17 over here. And 36 over here. So now our output is 17, 12, 23, 36, 62, 46, 41, 71, 55. Right? Make sense? So again, it's that whole up and down swapping thing. In any kind of sorting question like this will have some kind of multiple choice component on the exam so that I can auto grade it a lot faster. I've come to really appreciate multiple choices. The multiple choices are harder for me to write. They make the grading go so much faster. After the initial operation of Quadratic sort, how would this thing be sorted? So again, with Quadratic sort, we'd have the ones first. So 71, 41, then the twos, 62, 12, then the threes, 53, 23, and the fours place, there's no fours, then the fives, there's nothing ending with fives, then the sixes, there's two things ending with 6, 36, 46, and then anything ending with a 7 would go next, and 8s, 9s, and 0 and 10, or you could do the zeros first. It doesn't really matter because it will all get sorted. Well, you want the zeros first. So there we go. That's our answer for Quadratic sort. For bubble sort, who cares about bubble sort, honestly? Okay, how would the initial array be ordered for bubble sort? And then after the initial iteration of selection sort. So again, they're saying one pass. So with bubble sort, we don't really care about, but you basically, again, it's talking about after we swap, we wouldn't swap 17 or 53. We wouldn't swap these two. We would swap 62 and 71 with bubble sort. and then we'd swap the 71, and then 71 we keep swapping up all the way. With selection sort, that's actually even easier. We find the smallest item. So 17 is currently the small, 17 is currently the small, 17 is 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 smallest, 17 is smallest, 12 is the smallest. We've got to the end, so let's move the smallest item to the front by swapping it with the thing at the front. It just happened to be 17. That's just an interesting coincidence. That's it for selection sort. Selection sort's super easy, but it always takes O(n) squared time. But swaps are minimal. Here's another copy of the initial array. Oh, how nice. After the heap creation of the phase of the heap sort, how would the array be ordered? Your answer should be in an array, not a tree. We did that already with the previous question. I don't see a need for us to do it again unless anybody's particular. After 2 iterations of insertion sort, how would this array be ordered? Insertion sort, boom. That's the first iteration. That's why they want 2. Second iteration, boom. There, that's how it would be ordered. Okay, after 3 iterations, boom. What about 4? 4 iterations, it would look like this. It would look like 17, 53, 62, 71. Not like that. Okay. After the first iteration, the first item is sorted. After the second iteration, the second 2 items are sorted. At the third iteration, the third 3 items are sorted relative to each other. They're always sorted relative to each other as we go up the iterations. Make sense? This is what makes insertion sort pretty efficient, because as you saw, I was able to say done, done, and done for the first 3. Because if there's natural runs, we get to exploit them. And it becomes really nice to do that. And because a lot of data we collect is sinusoidal in nature, right? Distances of objects in space moving back and forth between us, or the temperature throughout the day, right? The temperature doesn't really do, the temperature doesn't look like this. Certainly not. That would be weird kind of imaginary temperature. It's always, it gets hotter, and then maybe you might have a cold dip, and then it gets warmer again as it heats up. And then as the day goes on, it goes down to nighttime and then heats back up. And, it's got these really nice natural kind of ascending and descending peaks. And insertion sort's really efficient at sorting that kind of stuff, which is why it gets used in Tim sort. Okay. Let's say you would like to sort a collection of data that's be sorted on a singly linked list. Why would shell sort be a good algorithm to adapt for this problem? Why or why not? Short answer, no. Long answer, no. Okay, and that is because with shell sort, what you do is that you have this gap factor for shell sort. So suppose we have this array of items. Right? What shell sort does is that it goes up, basically is that like it will go over, okay, let's insertion sort these guys, and then we're going to insertion sort these guys, and then we're going to insertion sort these guys, and it keeps going down until we get to the last item. But that last run of insertion sort actually goes ridiculously fast, because again, we've kind of created these natural runs that we're so good at exploiting. Insertion sort is confusing as heck in terms of runtime, because we don't know what it is. Like literally, it is an unsolved problem. It is not called shell sort because we're creating these shells of items to sort, which is I initially thought, but because the guy was named Shell, Donald Shell, which really seems like a lost career. He should have been a herpetologist studying turtles, in my opinion, with a name like that. Really missed his calling. But you can watch the animation to kind of see how it just kind of exploits these natural runs. Its complexity is an open problem in computer science. If you want some kind of award, if you want some kind of notoriety, be the person to figure out what the minimum is, because we found out what the run times would be for certain things, like n log n square. If your successive gaps are 2 to the p to 3 to the q, or if you're using these equations, then we can get n to the 4/3 power for the sorting time, which isn't as good as n log n. N log n is amazing. That is how good, but that's n times, and just in case you're curious what that means, that is n times the cube root of n. Okay, that's what 4/3 is. It's n times the cube root of n. Okay. Then you've got this nonsense. So shell sort as, and this all depends on what your gaps are, right? And this is what I mean. Like, you're sorting every number, then how far apart are your sequences. So why is this a bad algorithm for linked lists? Because if we're trying to swap, because swapping things that are very far away in linked lists is awful, because you'd have to do a lot of iterating, searching back and forth to get to those positions. You can't just jump to positions like you need to with the gap when there's gaps. Okay. 2, memory diagram. I don't want a memory diagram. You don't need this. Shift right, don't care. We're moving on. Okay. Index, not important for us. Okay. Then it's asking for 2-3 tree. Good. All right. So part 3, again, some parts of this are relevant for us because different classes cover different things. Once I finish writing this darn textbook, which I don't work on because this semester has been terrible. We're trying to get work done. I'll probably figure out a different curriculum for this course, but all right, suppose the middle key row of a standard keyboard, A, S, D, F, G, oh God, that's my password. Oh, darn. So are inserted in succession into an initially empty binary search tree. Draw the tree after this sequences of insertions have been made. So I assume it's going to be alphabetical for a binary search tree. So with A as the root, we're already in a kind of not great place because this big small signs at the root. So everything is going to be greater than that. So A, S, D comes before S, F comes after, before, after, G comes after F. Yeah, you see where this is going. H, and then J, and then K. Yeah. Ta-da! Right. It's a very unbalanced tree. I'm going to keep it here just in case. Given your answer to part A, what would the tree look like after performing the following operations? Insert. Okay. Oh, you really want to torture me now. Okay, insert B. So comes after, before. So B would go over here because of course it would. E comes after A, before, after, before. Remove A. Well, so much for getting the next in order predecessor. So we're going to have to go for the next in order successor, which means B, which is easy enough to deal with here so to do that, we go 1 to the right, and then we get all the way to the left, and that got us B, the next in order successor. Now to remove D, again, we're going to go 1 to the right, we're going to go all the way to the left, because that's just the way the tree is constructed. Because we can't get the net, and then E goes over here. Not really as much of a mess as it could have been. Okay. Now it wants us to do a 2-3 tree. So, the professor emphasized 2-3 trees there. So we don't need to worry about 2-3 trees, just know that they're balanced. Okay, this part definitely relevant to our exams. Hint, hint, nudge, nudge. Okay. You are given an initially empty sequence, an empty hash table of size 7. So we're not going to resize this hash table that uses open addressing, right? Open addressing, that means look for the next spot. Make sense? Look for the next spot. but we define next in different ways. Here we're defining that as linear probing versus quadratic probing. Make sense? So the following sequence of keys is to be inserted into this hash table. So 15, and so the hash, so insert the keys using the following approaches, where our key is where a key X goes into X mod 7, okay? And then resolve any collisions using linear probing. Okay, makes sense to everybody? So if you're not sure, you just follow along and you'll get it, okay? So 15, where do we need to put 15 in this hash table? Phil, 15, what is 15 mod 7? It's 1, because I've been doing modular arithmetic enough in my head to know that 15 divided by 7 gives me a remainder of 1, right? So 15 is going to go over here. What about 17? 17 divided by 7 gives you a remainder of, well, 14 is the closest number. So 14, 15, 16, 17, 3. 8. What is 8 mod 7? 8 mod 7 is 1. 8 divided by 7 gives you remainder 1. So 8 wants to go to index 1, but it can't because it's already taken, right? So linear probing, the way it resolves that is look for the next available space, with the next being defined as literally the next space, please. Make sense? Okay. 8 goes there. 23. 23 is X mod 7. So 23 mod 7, 21, 22, 23 wants to go into 2. 22 wants to go, sorry, 23 wants to go here. It can't. So it's going to try to go here, but it can't, so it's going to go here. Make sense? Now 3 mod 7 is pretty easy to calculate. It wants to go, 3 wants to go here, but it can't, so but it can't go here, so it goes to the next one. Ta-da. And 5 wants to go here, but it can't, so. And so our answer is 15, 8, 17, 23, 3, 5. And again, if we would go out of bounds, we simply we just simply start again at the beginning. Now, quadratic probing. Here, basically what we were doing is we're looking at linear probing. It looks for the next available space. Is mathematically defined as looking at our space plus z. If we can't have space plus 0, I'm going to take space plus 1. Then I'll try space plus 2, then space plus 3, then space plus 4. Quadratic probing says if I can't have space 0, then I'm going to try space plus 1 squared, then space plus 2 squared, then space plus 3 squared, and space plus 4. It doesn't mean move 1, then move 4, then move, from you aren't going to, so if you do it, you're not going to be 5 away from the initial space is the point. You're going to be 4 away from the initial space. Okay. Although the other one, if that would be a reasonable interpretation if you wrote it down. Okay, so again, first kind of operation, because we're using mod 7, come out as the same, 15, 17, and then we get a collision again. So I'm going to look 1 squared away, which is 1, so 8 will go over here. Make sense? So now here's where it changes. 23. What is 23? 23 is 23 mod 7 is 2, 23, sorry, 21, 22, 23. Okay, so it is going to be, so we're trying to go, 23 is trying to go here, but it cannot. So it looks 1 away, but 1 away doesn't work. So we are going to look 1, 2, 3, 4 away, right? Notice that it is 20, it is 1, 2, 3, 4 away from its initial place. So that's empty. So we're going to go here. Now we'll try to put in 3. 3 will look over here. And then 5 is already empty, so we can put that there. So what the advantage of quadratic probing is that it creates gaps. So when there are collisions, there's less individual steps to resolve. And because you have these nice big gaps, there's less likely to be collisions in general. Disadvantage is that we have added by adding a square operation, when we're dealing with constant time kind of operations, we really care about the number of operations that are in there. This was just simply you know, we've got an addition operation here, but here we're going to be doing a addition plus a multiplication operation, right? 1 squared, 2 squared, 3 squared, unless you have that programmed in, but in which case you're burning more memory, but that's okay. Burning more memory is fine because that's the entire point here. Here, this is not something we learned, but it's pretty easy to understand. I'm not going to go through with it because we're pretty much done with class, believe it or not. Here we're resolving using double hashing, which is, and I'll get to you in a second, which is that if the first hash function doesn't work, use the second hash function. Yes. Because that's 1 squared. Because the next one is 1 squared, then it'll be 2 squared, then it'll be 3 squared. That's why I chose the next one, because I was technically checking 1 squared away. Okay, so what other things? So I would go ahead and try these. So I'm going to go ahead and give you if you have the time, try these on your own. Because I'll be doing these graph algorithms on Thursday. I'll do this where we're going to be doing breadth first search and depth first search and Dijkstra's. It looks like they want to do the knapsack problem over here. We aren't going to just look this up. It's an awesome problem. I think I've told you it. It's the loot problem, where basically we are trying to stuff as much stuff into our backpack as a certain value, right? If we're tomb raiding, we can only carry so much loot. We want to carry the most valuable amount of loot that we can possibly take. And then over here, pseudocode for your reverse level algorithm. We'll also go over these coding things over here. I will definitely be spending Thursday trying to do more code. And if we don't, when is our exam? Thursday? Is it not? It's Tuesday, I believe. Let me check. Sorry, no. Thursday. Right, it's Thursday. So I'll double check. But if I don't have the time to get to everything that I want, I will host a study session I will host and record a study session during the study days. Okay? Because I want to make sure that everybody has the chance to succeed on these. Also check out the other exams link, especially like these directed graphs. I'm going to try to get to one of each problem that I can. There's a hash table problem. I definitely want a code that's not listed, which is given a list of usernames and their login times, just logs. So there's multiple entries for each user. Give me the average number of time, output a dictionary containing hash table containing the average number of time that each user has been logged in. So Alice has been logged in her sessions on average last a minute. Bob's last on average 10 minutes. Make sense? That is the kind of problem we will be working on. And I'll of course add my own spice to it by making it by actually pretending to read a fake file. Okay. So with that, it is 10:50. Again, if you need to meet with me to demo stuff and you do not have the opportunity to do so, please just send me an email or send your TAs an email to meet with them. That's perfectly fine, especially since the last project is due. Yeah. I'll also be happy to meet with you during the study days, but also I'm available pretty much every evening up through and including 10 o'clock, most evenings. So just send me an email. If I don't get back to you, it's because I'm dealing with 27 academic dishonesty complaints I had to fill out for 1051.